In this video, we will talk about solution sets for linear systems. In particular, a system of linear equations can either have infinitely many solutions, no solution, or unique solution. We will do an example of infinitely many solutions, of an overdetermined system, and many other examples. We will not be covering Gauss-Jordan elimination except to say that it is a method of solving systems of equations that involves using the elementary row operations we normally do to get the Gauss elimination form, the upper triangular form, but it further reduces it to the given system and then eliminates the need for back solving. We will start by looking at a system of linear equations and noting that a system of linear equations can have three possible situations. One, it can have infinitely many solutions, no solutions, or a unique solution. And to see this, we're going to do a geometric example. And so that it's easy to draw, easy to see, we're going to do two linear equations, equations of two lines, and two unknowns. So this is our first case here. If we have our two linear equations, such as x1 plus x2 equals 2, and 2x1 plus 2x2 equals 4, you can see these two equations represent the same line. And so there are many, infinitely many solutions. So over here at x equals 2 and y equals 0, that's one solution. We also have the solution x equals 0 and y equals 2. And over here at x equals 1, we have y equals to 1. So there's, I just named out three solutions, but any point on this line would be a solution. So we can have infinitely many solutions. And the two equations representing the same line, it's easy for you to think about here when I've mentioned it to you, but it's something you want to keep in mind because I know once someone asked me about two different equations and I forgot about this case when the equations represented the same line, so I lost points on one of my quizzes. And I've not made that mistake again, but I'm going to warn you so you may actually be saved from making that a mistake ever on any quiz or exam. The second situation here is no solution. So you can see if you have two parallel lines, x1 plus x2 equals 2 and x1 plus x2 equals 1, that there's no intersection. So there's no xy or x1, x2 points that will satisfy both this first equation and the second equation. So the next, again, situation is no solution. The final situation is a unique solution. So you have intersecting lines. So the lines intersect at exactly one point. So for example, x1 plus x2 equals 3 and x1 minus x2 equals 1. So intersection at a single point or a unique solution. So these are the three cases you have. You want to take a look, you want to convince yourself that there's no other possibility other than infinitely many, no solution, or unique solution, at least for the two linear equations, two unknowns. And then you want to remember in general, these are the three situations you can have for any set of linear equations. Next, we will do an example of infinitely many solutions. Now we have a 3 by 3. So I have x1 minus 2x2 minus x3 equals negative 2. 2x1 plus x2 plus 3x3 equals 1. Minus 3x1 plus x2 minus 2x3 equals 1. And again, I use this notation. The e2 means we're replacing the second equation, and we're replacing it with e2 minus 2e1. So if I multiply e1 by negative 2 and add it to e2, I get my 0 for my second equation. Minus 2 would be it would be positive 4, plus 1 would be 5x3. Here I have minus 2 times this, so I'll get positive 2, plus 3, I'd get 5x3. Minus 2 would be 4, plus 1 would be 5. So that's my second line. And then my third equation, and I know it's the third equation I'm replacing because E3 is first, but it's replaced with E3 plus 3E1. So multiplying by 3 and adding, I get 5x2 minus 5x3 equals 5. And then I replace the third equation with E3 plus E2. So adding these together, I have my 0x2, I have my 0x3, and then I have 0. So what I have is 0x3 equals 0. Well, any x3 will satisfy this condition here. So there are no restrictions on x3, and it's what we call a free parameter. So now if x3, we're going to solve for x2 and x1 in terms of x3. So once we choose x3, then that will determine x1 and x2. So here I have 5x2 plus 5x3 equals 5. So x2 that gives me x2 is equal to 1 minus x3. And I also have x1 minus 2x2 minus x3 equals minus 2. So solving in terms of my free variable x3, that gives me x1 is equal to, moving this over, 2x2 plus x3 minus 2. And then I substitute for my x2, that's equal to 1 minus x3. So finally I get x1 is equal to minus x3, which means I have an infinite number of solutions because I have an infinite number of choices for x3. Once I choose x3, say for example I choose x3 equals 0, then x1 is equal to 0 and x2 is equal to 1 minus 0, which is just 1. And then if you want to check your solution, you can always plug it into the three equations. And just to repeat, so this is an example of infinitely many solutions where we have one variable with no restrictions, a free parameter, and then the other variables are solved in terms of our free parameter. Next, we are going to have an example of no solutions, and in particular, we're going to do an example of an overdetermined system. Overdetermined means there are more equations or more constraints than unknowns. So we have x1 minus x2 equals 3, 2x1 plus x2 equals 6, and x1 plus x2 equals 1. Again, it's overdetermined because we have three equations but only two unknowns, so more constraints than we have unknowns. So first, again, for our notation, our second row, E2, our second equation, is replaced by E2 minus 2E1. So here for the second equation, I have 3x2 equals 0. And our third equation now is replaced by E3 minus E1, so that will give us 2x2 equals minus 2. So this system is inconsistent because here the second equation will require that x2 equals 0, whereas the third equation would require x2 to be equal to negative 1. So there's no way that this system of equations, there's no x2 that can satisfy both the second and third equations. So the second and third, they're inconsistent, and the system of equations has no solutions. There are other examples of no solutions that are not overdetermined. For example, this equation x1 plus x2 equals 2 and x1 plus x2 equals 1 is also not overdetermined, but there is no solution. And just to remind you, an example of a unique solution, I have this 2 by 2, so I have x1 plus 2x2 equals minus 5, 2x1 minus x2 equals 5. I replace E2, the second equation, with E2 minus 2E1 over here, and then I get from solving for x2, I get x2 equals minus 3. When I plug this minus 3 into this equation to solve for x1, that plugging back in backwards going up the chain to solve for x1 in terms of x2 is called back solving. I usually don't use that term back solving, but just in case someone says it, you'll know what it means. I have three more example problems. The first one is two equations and three unknowns. And before we had more equations than unknowns, and that was overdetermined. So in some sense, when we have more unknowns than equations, this is sort of underdetermined. So we're expecting a free variable. So the equations, my system of equations is x1 minus x3 equals 1, and then my next equation is x2 plus x3 equals negative 1. Now if I try to eliminate one more variable, for example, if I replace E2, the second equation, with E2 plus 1, so I'm trying to eliminate this x3 variable, you see when I add these two, I'll get x1 plus x2. I eliminate the x3 and then I get 0. But I still have two variables. So, there's just no way I can eliminate so that I have only one variable in one of the equations. So I cannot simplify this any further. So what I can do is I can make one of my variables free, and I'll make my x3 variable free. Just for whatever reason, often I make my last variable, the variable with the highest index, free. So if x3 is free, that means that x1 will be equal to 1 plus x3, and x2 is going to be equal to negative, where's x2, is equal to minus, using this first equation, is equal to minus 1 minus x3. So for example, if I set x3, my free variable, equal to 0, and I almost always, if I need an example solution, I almost always set my free variable equal to 0, because why not? It'll give me easy numbers to work with. That will mean my x1 will be equal to 1, and my x2 will be equal to minus 1. And I can plug these in and see that my equations are solved. And again, for every choice of x3, I have a new set of solutions. So there are an infinite number of solutions because there are infinite number of ways of plugging in for x3. My next example is 3 equations, 5 unknowns. So again, this is going to be more unknowns than equations. So I have 2x1 plus x2 minus x3 minus x4 plus 2x5 equals 3, 2x2 minus 2x3 plus x4 plus x5 equals minus 1, and x3 plus 2x4 minus x5 equals 2. And you can see it's in triangular form because our first equation has all the variables. The second equation eliminates x1, and the last equation eliminates x1 and x2. So this is as simple as it gets. So in this case, I can solve for x3 in terms of x4 and x5. In other words, because this has 3 variables, 2 of them must be free, and I'm going to choose x4 and x5 as free. And then x3 can be solved as this 2 minus 2x4 plus x5. And x2 can be solved as my minus 1. Moving over, I have plus 2x3 minus x4 minus x5. But then for x3, I can plug in my 2 minus 2x4 plus x5, so that x2 can be solved simply in terms of x4 and x5, and it's 3 minus x4 plus x5. You can look at the algebra here if you want. And then my last equation, again, or up here, my last equation, x1 is equal to 3 halves plus 1 half, my minus x2, my plus x3, my plus x4, and my minus 2x5. Again, all of this multiplied by 1 half. And if I plug in for my x2 in terms of 4 and 5, and my x3 in terms of 4 and 5, so that I can get x1 only in terms of 4 and 5, I have 1 plus 2x4 minus x5. And then, so there are infinite number of solutions because there are infinite ways of plugging in for x4 and x5. And then I did plug in x4 equals 0, and x5, just for variation, I plugged in 1. It's still easy numbers, and this is one set of solutions. And I have one more set of equations, x2 plus x3 minus x4 equals 0, x1 minus x2 plus 3x3 minus x4 equals minus 2, x1 plus x2 plus x3 plus x4 equals 2. So I swap equation 1 and 2 because I want the top equation to have x1. And now my second equation eliminates the x1. So this equation here, I want to eliminate x1 and also x2 eventually. So I am going to substitute for E3. I'm going to substitute E3 minus E1. And that will give me, that'll eliminate x1, and it'll give me 2x2 minus 2x3 plus 2x4 plus 4. Now I want to eliminate x2 for my third equation. So I'm going to replace E3 with E3 minus 2E2, and I get this equation here. So at the end, I have my triangular form, and I have x3 and x4. I have one equation, 2 unknowns, so one of these has to be free. So I'm going to choose x4 to be free, solve for x3, x2, and x1, and I'll let you look at the algebra. Now I have an additional problem, which is to find a solution with x3 equal to 0. So if I set x3 equal to 0, I can see that x4, if x3 is 0, is equal to 0 plus 1. So I have 1. x2 will always be equal to 1. x1 here, again, is equal to 2 minus x4, which I have already solved for, is equal to 1. So that's also 1. So here is 0, 1, 0, 1 is a solution with x3 equal to 0. In this video, we looked at the possible scenarios for solutions of linear systems. We can either have infinitely many solutions, no solution, or unique solution. We did many examples of infinitely many solutions, and we also looked at that graphically, infinitely many, graphically, what that might look like. We looked at no solution, which we did at least one example of that. And then we also have this graphical example, so 2 examples. And then we did unique solution, which we have one graphical example of. And in our previous video, we had many unique solutions. I did want to mention Gauss-Jordan elimination is something we didn't cover, but it is a method of solving systems of equations the way we use Gaussian elimination. But this one kind of keeps going. You keep doing elementary row operations to make it even further reduced, but we're not going to cover that. And that's it for this video. Thank you for watching.